All right, let's talk about something that, let's be honest, can feel super intimidating. The fundamentals of electromagnetism.
Yeah, looks complicated, doesn't it? I mean, with over 37 variables, 50-plus equations, it's a beast. But what if I told you that underneath all this chaos, there's a beautiful, elegant system, a logic that once you see it makes this whole thing click?
Okay, so how do we even begin to tackle this? Well, we need a strategy. We need a map. And this is our map. We're going to use a really powerful learning technique called Trinity memorization, or TM for short. Think of it as our secret weapon for conquering this complexity.
So let's talk about this strategy for climbing the mountain, the TM framework.
So here's the core idea of Trinity memorization. You link three things together. First, the theoretical rationality, understanding the actual physics of what's happening. Second, the mathematical consistency, getting a handle on the formulas. And third, dimensional analysis, which is just a fancy way of saying making sure the units make sense. The magic here is that they're all connected. If you forget one piece, say a formula, the other two, the theory and the units, can help you figure it out again. It's like a built-in error check for your brain.
Okay, next up, the language of fields, vector analysis as a tool. Now, before we can really use our map, we've got to learn the language it's written in. And for electromagnetism, that language is vector analysis. But here's a really, really important point. Vector analysis, all these weird symbols we're about to see, they're just tools. They're the grammar we use to describe the physics. They are not the story itself.
And our main tool is this guy right here, the nabla operator, that upside-down triangle. So what is it? Well, it's basically a vector operator that tells us how things are changing in 3D space. It's a way to measure change. And look at its units, 1/meters. That's a huge clue. It's all about how much something changes per meter of distance.
And this tool lets us understand a really profound and honestly beautiful idea called Helmholtz's theorem. It says that any vector field, no matter how crazy and complicated it looks, can be broken down into just two basic things. First, a divergence component, think of this as sources or sinks, and second, a curl component, which is all about rotation or vortices. The perfect analogy is a bathtub. You've got water coming out of the faucet, that's a source, that's divergence. Then you stir the water with your hand, you get these little whirlpools, right? That's curl, that's rotation. And get this, Maxwell's equations are built directly on this principle. It's why there are 4 of them.
So let's break that down. Divergence, that's the nabla with a dot product, measures the outwardness from a point. Is stuff flowing out or flowing in? It gives you back a single number, a scalar. Simple. Then you have curl. That's nabla with a cross product. This measures the rotation at a point. Is the field swirling around? And because a swirl has an axis of rotation, the answer has to be a vector. It has both a magnitude and a direction. That's it. Sources and swirls. Those are our building blocks.
All right, so we've got our language, we've got our tools. Let's move on to the main event, Maxwell's beautiful blueprint, the EDBH framework. Okay, here it is, the EDBH framework. This is the heart of it all. It beautifully organizes the 4 main variables. You've got the electric field, E, and the magnetic field, B. And then you have their buddies, D, the electric flux density, and H, the magnetic field intensity. See how they're all connected in this nice, simple loop?
And here's where it all comes together. The 4 Maxwell's equations, they're not just 4 random laws, they're simply the rules that tell us about the sources and the swirls for both the electric and magnetic fields. See? 2 equations for divergence, the sources, and 2 equations for curl, the swirls. It's that Helmholtz theorem in action. It's so elegant.
And this beautiful symmetrical structure wasn't just for show. It actually led to one of the biggest aha moments in the history of science.
So, picture this. It's the 1860s. James Clerk Maxwell is trying to put all the known laws of electricity and magnetism into one neat package. But there's a problem. One of the equations, Ampere's law, just doesn't quite work in all situations. It had a little inconsistency. So to fix it, he adds this tiny little term. He called it the displacement current. At the time, it was basically just a mathematical patch to make the theory consistent. But that one little fix, it changed everything. It led to this incredible prediction. His new, complete set of equations predicted that waves of electricity and magnetism should be able to travel through space. And not only that, he could calculate their speed. And to do it, he used 2 constants that seemed totally unrelated, epsilon naught from experiments with static electricity, and mu0 from experiments with magnets.
So he crunches the numbers, and what does he get? A speed of about 300 million meters per second. And you have to imagine him looking at that number and just freezing. Because that number was already famous. It was almost exactly the measured speed of light.
The conclusion was just inescapable. Light is an electromagnetic wave. In that single moment, electricity, magnetism, and light, three things that seemed totally separate, were unified into one single glorious phenomenon, absolutely world-changing.
Okay, so now let's bring it all back home. We're going to see how the puzzle comes together and master the map.
And here's where our Trinity memorization strategy really pays off. Remember that third piece, dimensional analysis, checking the units? Well, now we can apply it. We can literally trace the units all the way around this EDBH loop through every single equation. And when you do, you find that the system is perfectly, flawlessly consistent. The units on both sides of every single one of Maxwell's equations match up. It's beautiful. And it even reveals this cool hidden symmetry. See how the variables on the left, E and B, are all volt-based, and the ones on the right, D and H, are ampere-based? And this framework, this is just the beginning. It's the foundation for more than 40 other equations that all plug into this same system.
So, what did we accomplish here? Well, we started with what looked like an impossible mountain of complexity, right?
But look at this chart again now. It's not just a mess of symbols anymore, is it? You can see the structure. You can see the EDBH framework at its heart. You know that the equations branching off are just describing sources and swirls. This isn't just a scary diagram anymore. It's a map. And now you have the strategy and the language you need to start reading it. A new journey begins.
It kind of makes you wonder, right? What other incredibly complex systems out there could be understood if we just find the right underlying framework? Anyway, something to chew on. Thanks so much for joining me on this explainer. Keep learning, and we'll see you next time.